Hello, guys. Welcome back to BioBuzz. This is episode 2, where we're getting very, very tiny, subatomic. We have a new co-host today. Why don't you introduce yourself?
Hello, everybody. My name's Eric. I'm a biochemistry major at Marshall. I'm super excited to be here today.
Okay, do you want to introduce what we're going to talk about today?
Yeah, so we're going to get really tiny today, like subatomic tiny. We're going to be diving into atoms, molecules, and bonds, really things that, hold life together.
hmm If that sounds intimidating, don't worry. We're not about boring lectures or endless memorization here. We're going to be making this fun, relatable, and just the right amount of nerdy.
And quick too. You can think of it like this. It's a science class meets a coffee chat with your friends. Except today we're going to shrink it down to explore the scale of life, from the nucleus to the molecules and bonds. Think of it like, when you're driving here or when you're heading to class, just taking a listen at this before your lecture or maybe even after to help yourself review.
Let's go ahead and dive into segment 1, size scale. So let's set a stage. Imagine you're in your typical college lecture hall, one of those big ones that can fit like 400 people. Now shrink yourself down and step inside. That's essentially a human cell.
Huh. What would that even look like?
Okay, picture this. The nucleus would stretch almost to the top of the ceiling. It's the control center, so obviously it gets the prime real estate.
And what about the mitochondria
Those are kind of like life rafts. They float around the room, powering everything.
and ribosomes?
Um, I would, I'd say about the size of a golf ball, just bouncing around everywhere, assembling proteins like tiny factory workers.
Hmm. And what do you think about proteins?
I would say a marble. So now you've got your life raft, your golf balls, and your marbles all packed into this one room.
And if we go even smaller, what about water molecules?
Those would be like poppy seeds just zipping around. Um, Honestly, it's kind of wild to think about how this is all crammed into a single cell, huh?
Yeah, it is. So now that we've got this visual, let's talk a little bit about the building blocks of life. Where does it all begin here?
With matter. Matter is everything that takes up space and has mass. So basically, all the stuff in the universe.
hmm And it's made up of elements, which are pure substances containing one type of atom. For example, gold is made entirely of gold atoms. In this class, we mainly see the same four elements: carbon, hydrogen, nitrogen, and oxygen. You can think of it as CHNO and just kind of memorize it by their first letters, probably the easiest way to do it.
hmm
These are the most naturally occurring in biological life, aka living things. They're all around us. They are in us too, as the human body, and they're in most animals and obviously all plants and life.
However, we don't just see elements in a single form. They're different when it comes to two or more atoms bonded together. This is what we call a molecule.
Yeah. And if those atoms are from different elements, like water, you got a compound.
So, a good way to think about it is molecules are like Lego bricks and they snap together, while compounds are when those bricks are different colors.
hmm and what about the bonds that hold all these atoms together?
Bonds are the forces that keep atoms together, and there are really only three we go over: covalent, ionic, and hydrogen bonds.
Cool. Let's start with covalent bonds. These bonds are only seen within nonmetals like carbon,
Mm.
hydrogen, etc. And these bonds are all about sharing.
hmm It's like a friendship where two atoms share electrons to stay stable.
Yeah. And there are two types. There's nonpolar and there's polar. Nonpolar covalent bonds, they usually share electrons equally. It's kind of like splitting snacks down the middle.
But polar covalent bonds are more like when one friend always keeps the bigger piece of the cookie.
Yeah, and that friend is usually oxygen or nitrogen. They're super greedy for electrons. And this is because every element has a certain level of electronegativity based on the amount of electrons it has naturally. Don't worry about that. We don't really need to memorize all 118 elements right now. For build one, you really just have to know that carbon and hydrogen have the lowest amount of electronegativity, while nitrogen and oxygen have a much higher level of electronegativity. So as the order goes, carbon, hydrogen, nitrogen, then oxygen, CHNO. This is super important, so make sure you know it. It's going to be on most of the midterms, definitely going beyond the final from our experience. For
Yeah.
example, if carbon is bonded with oxygen, since oxygen has a higher electronegativity, it would take most of the electrons, resulting in two things. Number one, a polar covalent bond, and second, a partial positive charged carbon, since most of its electrons are being used by oxygen, and a partially negative charged oxygen as it hogs the electrons. For those who've already done something similar or have learned this in high school, you can double check this by referencing a electronegativity chart. You'll see by just taking a look at that the bond between carbon and oxygen has such a big difference that you can see why oxygen would hold more electrons and carbon hold less. If the molecule, though, is charging the electron equally, so nonpolar, it wouldn't have any partial charge since charges only occur when the electron is stealing electrons or losing electrons.
Mm-hmm. And that's a mouthful, but I'll take it as my turn now because we're going to go into ionic bonds now. These are much more dramatic. It's kind of like a breakup where one atom completely gives up an electron and the other takes it. Like your ex that just won't get back your stuff. This is a complete transfer of electrons.
So they're not sharing at all.
Nope, but that transfer creates two ions with opposite charges, one positive and one negative, similar to how covalent bonds have partial positive charges, but because this is a complete transfer, it's not a partial charge, it's just a complete charge. But this, as we know, opposites attract, and this is how we get elements like table salt, sodium. I said elements. I'm going to go back and correct myself. I meant to say molecules. This is how we get sodium, chlorine, methine, etc. And these are how they bond together.
hmm And what happens if you hypothetically toss salt in water?
Well, the water molecules get in there like tiny referees, breaking up these ionic bonds, and it breaks. Ionic bonds are water soluble, so when they're put in water, they completely break up.
I see. Okay, well, let's get into hydrogen bonds then. These are a little bit more like gentle handshakes between molecules.
Yeah, but you don't want to underestimate them because hydrogen bonds are what hold DNA strands together and give water its incredible properties. They form through hydrogen partial charges. As hydrogen has a lower electronegativity, it's often left with a partial positive charge, making it attracted to negatively charged elements. This is how water molecules bind together. In H2O, hydrogens are left partially positive and oxygens are left negative, partially negative, just due to the electronegativity. And this results in a nearby hydrogen becoming attracted to the oxygen in an H2O molecule. And this kind of results in an ongoing chain of hydrogen bonds within water.
Speaking of water, let's analyze another one of the important molecules that you're learning in this class. And specifically, let's talk about why it's so amazing.
Well, first, water is polar, which means it can dissolve a ton of substances. Scientists even call it the universal solvent.
hmm And that means it's hydrophilic. It means that water loves substances like salt, and salt loves water, and they, because of that, dissolve really easily. On the contrary, though, you have something like hydrophobic or water-fearing substances like oil or water haters, and therefore they repel it.
This is why oil and water don't mix, and it's also why water can carry nutrients, breaking down molecules, and basically keeps life running smoothly.
How do you know if a molecule is hydrophobic or hydrophilic?
Well, hydrophobic molecules are nonpolar. A trick to remember this is to remember nonpolar molecules are non-water loving, leaving polar molecules to be hydrophilic, the opposite.
hmm Okay, so we've talked about atoms, molecules, and bonds. Why should anyone care?
Well, because of these tiny interactions, they shape pretty much everything in biology. For example, the way proteins fold and their function. It all really just depends entirely on bonds.
And when bonds break, things can go wrong. Think about diseases caused by misfolded proteins like Alzheimer's.
But that same sensitivity is what makes life adaptable. Proteins can change shape to respond to their environment, allowing cells to adapt and survive.
It's wild to think that something as small as an atom can have such a huge impact on life as we know it.
Exactly, but I think that's all we wanted to cover today on atoms, molecules, and bonds.
We really hope that this episode helped you to see how t these tiny building blocks create the complexity of life. And we hope that you kind of learned something. Either you're listening to this before your lecture, after your lecture, or maybe even when you're studying for a midterm. We hope that this information really helps.
And if you liked this episode, go ahead and follow us on our Instagram at BioBuzzer, only if you want to, or you could subscribe to our YouTube channel at BioBuzz Tutors. I also want to put out there that if you have any questions or concerns or any ideas that you want us to cover in our next episode, feel free to leave a comment on our Instagram or DM us. We're constantly looking for feedback for you guys because we want to make this the best experience for you guys.
And again, remember, science is messy, it's weird, but it's also incredibly awesome. Thanks for listening, and we'll see you next time for more BioBuzz.
Bye!